In this video, we work our second example involving intervals where the function is increasing and decreasing. We've got this function. It's got a square root in it. It's a composite function involving a polynomial and a function of the rational exponent. And then we take a product of that function and add. We would expect it to be continuous on its domain, but we're interested in where the function is increasing and decreasing. Now, we'll also use the first derivative test for this particular function to infer where our function has relative extrema, so a relative minimum or a relative maximum. So this is the formal statement of the first derivative test. It says, let's say that f is continuous on an interval I, and that interval contains a point C, and C is just a critical number of f. So remember, critical numbers are at x values where the derivative is either 0 or the derivative is undefined. If f prime changes from positive to negative at C, then f of C is a relative maximum of f. Now, I actually don't memorize this at all. All I do is think about what it means to have a positive slope and then to have a negative slope. So let's say our function goes from having a positive slope to a 0 slope and then a negative slope. So f prime is 0 at the top, f prime is positive on this side, and f prime is negative on this side. Well, then we can see that we have a relative maximum. Now, and this is where, this is the point, let's say, x equals C, y equals f of C. Now, and that's if our critical point corresponds to a point where, or corresponds to a 0 derivative. Now, it's also possible that our function could go from having a positive slope to an undefined slope to a negative slope. So f prime is undefined here, and f prime is positive on this side and negative on this side. Either way, x equals C represents a critical point, and either way, we have a relative maximum at that location. So if f prime is changing from positive to negative, f of C, that's the y value there, is a relative maximum of the function. Now, if the derivative changes from negative to positive at x equals C, maybe it would go from decreasing, having a 0 slope, to increasing, because having a negative derivative means the function is decreasing. We have a 0 slope at the bottom, and then a positive slope to the right of that. Then if this is the point C, f of C, we've got a relative minimum there. Now, similarly, if we go from, let's see, trying to draw sort of we could go from decreasing, having an undefined slope, to being decreasing. So, or increasing, f prime is negative, f prime is undefined. And then f prime is positive. Then at that point would be a relative min. So whether our derivative is 0 or our derivative is undefined, if our sign changes, the sign of the derivative changes at that x value, we have either a relative min or a relative max. Now, it's possible that f prime doesn't change signs at x equals C. So maybe at x equals C, our graph looks like this. So it goes from having a positive derivative to having a 0 slope, and then having a positive derivative again. And then that's just a flat spot. That's neither a min nor a max, because there are y values nearby that are smaller than it, and there are y values nearby that are larger than it. Of course, we could go the other way. Here, maybe we've got a 0 slope there. Here, f prime is negative, then f prime is 0, and then f prime is negative again. So that's neither a min nor a max, because there are y values that are larger than that y value, and there are y values that are smaller than that y value. So the key is that f prime changes signs. Now, when we make our sign chart, that's going to give us intervals where that sign of f prime is either positive or negative, like we did in the last example. We said y prime was positive on this interval, and then negative on this interval, and then positive on this interval. Since it went from positive to 0 to negative, that means our function goes from increasing to having a 0 slope to decreasing. So we've got a relative max there. And then at this location, our function goes from decreasing to having a 0 slope to increasing. So we've got a relative min there. That's called the first derivative test. And that the picture would change if those x values corresponded to x values where the derivative was undefined. We wouldn't have these sort of tangent lines with a zero slope. Instead, we'd have a cusp or something that looks like that. But still, if the derivative changes signs, we get a relative min or a relative max. One thing I added to this after I finished the video was the rest of sort of this procedure when you make your sign chart. Usually what we do is we compute y prime. After computing y prime, we're looking for the critical values. So we set it equal to 0 and solve for x. Now, most of the time, not always, but most of the time, the way to find x is to factor that y prime. So we write it as a product of a number of factors. And we say y prime is this times this, and that product is 0. And so the way we find the sign of y prime is we look at the sign of each of those factors on the intervals defined by the critical values. So the critical values come from setting the factors equal to 0 and solving for x. Now, those x values, those critical values, are the x values where these factors change sign. So 3x is negative when x is negative. It's positive when x is positive. X minus 4 is positive when x is greater than 4. It's negative when x is less than 4. And so we find the sign of each factor on each of the intervals, and then you multiply those signs to get the factor of y prime. The negative times a negative is a positive times a negative is a negative, and a positive times a positive is a positive. That allows you to infer these signs, and if y prime is positive, the function's increasing. If y prime is negative, the function is decreasing. And if the function or if the derivative changes signs, we either have a relative min or a relative max if it goes from positive to negative, or a relative min if it goes from negative to positive. Now, we want to include our critical values on this line, which include those values of x that cause the derivative to be 0 or the derivative to be undefined. And critical values also have to be in the domain of the function as well. Okay, so that's the first derivative test. Let's apply that to this function. So we've got y equals, or f of x equals if you prefer f of x, x times the square root of 16 minus x squared. And that's the same as 16 minus x squared to the 1/2 power. When we compute the derivative, we have to use the product rule. The product rule says the derivative of a product is the derivative of the first function times the second, undifferentiated, plus the derivative of the second function, undifferentiated, or differentiated, excuse me, times the first undifferentiated. The derivative of x is just 1. And the derivative of this piece requires the chain because I've got a function nested inside another function. So this is my inside function, and the outside function is that function raised to the 1/2 power. So when we compute that derivative, we'll have the derivative of the outside, derivative of a function to the 1/2 is 1/2 of that function to the 1 less power. 1/2 minus 1 is negative 1/2. You put the inside function back inside, and then you multiply by the derivative of the inside by the chain. And don't forget to multiply by that x. It's still there, you're just not doing anything with it. And this derivative is derivative 16, which is 0, minus the derivative of x squared, which is 2x. So we get a negative 2x there. And we can simplify this. The 1/2 times the negative 2 is a negative 1, and then we've got an x times an x, which is x squared. This is 16 minus x squared to the negative 1/2 power. And if you want to, you can rewrite this expression as x squared divided by 16 minus x squared to the 1/2 power. Because that negative exponent can be rewritten this way. This is 1 over the same expression to the positive 1/2 power. So I've got 1 over x squared times 1 over the quantity x 16 minus x squared to the 1/2, and then you multiply straight across and you get this. Now, in order to find the x values that cause this to be 0, it's best to get a common denominator. Since this denominator is 1, an implied 1, and this denominator is this, we're going to multiply the numerator and denominator of this expression by this. The least common denominator is just the only denominator that we have. So multiply by 16 minus x squared to the 1/2, divided by 16 minus x squared to the 1/2. You've got the square root of something times the square root of the same thing. So you're just going to get the expression inside. Because the square root of x times the square root of x is the square root of x squared, which is just x, right? And provided that x is positive. I guess I should say that. The absolute value of x. And then we're subtracting x squared from that. And we've got a square root of 16 minus x squared in the denominator. Now, since we're taking the square root of 16 minus x squared, the domain is implied. We're assuming that 16 minus x squared is positive anyway. So we'll say this is equal to 16 minus x squared, all divided by the square root of 16 minus x squared. Since this expression is, I should say, since 16 minus x squared is positive, or well, it's strictly positive. Is it strictly positive? No, it's greater than or equal to 0. On the domain of F, that's equal to 16 minus 2x squared, all divided by the square root of 16 minus x squared. And we can factor out a 2. So this is 2 times the quantity 8 minus x squared, all divided by the square root of 16 minus x squared. Okay. So that is our f prime. Now, the critical values correspond to x values that are in the domain, for which the derivative is either 0 or the derivative is undefined. Now, it's helpful to think about the domain of this function. Now, the only concern with this particular function is taking the square root of a negative number. That 1/2 power is a square root, and we don't want complex numbers as our answers. We want positive numbers or possibly 0. So the domain of y equals f of x is all x values such that 16 minus x squared is actually positive, or actually non-negative. 16 minus x squared has to be greater than or equal to 0. So we'll say the domain is all the set of all x such that 16 minus x squared is greater than or equal to 0. And if we look at that parabola, 16 minus x squared just looks like this, right? That's going to be positive whenever the graph is above the x-axis, and that graph is above the x-axis when x is between -4 and 4. So we're saying, when are we up here? When are we in that part of the graph? Well, whenever x is between -4 and 4, because when x is -4 or 4, y is 0. And then y is larger than that for all x values in between. So this has as its solution set. If we want it to be greater than or equal to 0, we'll have equal signs there. The domain is the set of all real numbers x, such that x is between -4 and 4. Or we can write this as the interval from -4 to 4. Okay, so that's our domain. And we want the critical values of this function on its domain. So we want f prime to be either 0 or undefined. Well, obviously f prime is 0, or excuse me, is undefined whenever the denominator is 0. So f prime is undefined when 16 minus x squared is 0, which means that x equals plus or minus 4. And we can kind of see that. Say f prime is 2 times 8 minus x squared, all divided by the square root of 16 minus x squared. So it's undefined when the denominator equals 0. And that means that it's undefined when 16 minus x squared is equal to 0, or when x squared is equal to 16, or when x is equal to plus or minus the square root of 16, which is plus or minus 1. So f prime is undefined at the endpoints of our domain. Now f prime is equal to 0 when the numerator is 0 and the denominator is not 0. The numerator is not equal to 0 at x equals plus or minus 4, so we don't have to worry about the case where we have a 0 over 0 expression. So we'll have f prime is equal to 0 when the numerator is 0. So that means that 2 times the quantity 8 minus x squared is equal to 0. So 8 is equal to x squared, which means that x is equal to plus or minus the square root of 8, or plus or minus 2 root 2. So those are our critical values, plus or minus 4 and plus or minus 2 root 2. So I draw my sign chart for f prime. Now normally we would have the entire number line here, but we won't have that this time. So our number line consists of the interval from -4 to 4, and we've got these two critical values, and these would be critical values, or these are critical values as well, because they are in the domain of the function and the derivative is undefined there. And f prime is actually this quotient. It's this times this divided by this. So we'll look at the sign of each of those factors. So f prime is 2 times the quantity 8 minus x squared, all divided by the quantity 16 minus square root of 16 minus x squared. Now in all of these intervals, this is an interval of x values. No matter what x is, 2 is always positive. So we're gonna get positive, positive, and positive there. And no matter what x is here, the square root of a number is always positive, except for when it's 0, and it's 0 at the endpoints. So we're gonna have a positive answer, and a positive answer here. But on this interval, well, the only term that changes signs is this 8 minus x squared. And actually, it's helpful to look at that graphically. Again, we've got another parabola that's upside down, right? We've got y equals 8 minus x squared. And here's negative 2 root 2, and here's positive 2 root 2. We can see that 8 minus x squared is negative from negative infinity to negative 2 root 2. So it's going to be negative on this interval. It's positive between negative 2 root 2 and positive 2 root 2. And then it's negative on the interval from 2 root 2 to infinity. And so you can choose a test value, an x value in this interval, and substitute it into this function. Here I could choose x equals 8 and x equals 0 and substitute into this function 8 minus 0 squared is 8, which is positive. But rather than doing that, I think it's simpler, at least for me, to say that's just a parabola. And I know where that parabola crosses the y-axis. So I can just look at the y values of this graph and say the y values are negative here, positive here, and then negative here, to infer that these signs should be negative, positive, then negative. Now f prime is this times this divided by this. So it's a positive times a negative divided by a positive. So that's going to give us a negative sign. And then we've got a positive times a positive divided by a positive, which is positive. And then positive times a negative, which is negative, divided by a positive, which is negative. So f prime is negative on this interval, positive on this interval, and negative on this interval. That means our function is decreasing here and increasing here. So f is increasing on the interval from -4 to -2, or I said increasing. Decreasing on the interval from -4 to -2 root 2, and decreasing on the interval from root 2 to 4. And then f is increasing on that interval in between from -2 root 2 to +2 root 2. And that's our answer to the first question. Now, we know that we can also use the first derivative test to infer whether these x values correspond to relative minima or maxima. Now, we know that the derivative is 0 here at x equals plus or minus the square root of 2 because we did this calculation. So since our derivative goes from negative to 0 to positive, the function goes from decreasing to having a 0 slope to increasing. We've got a relative min there at x equals negative 2 times the square root of 2. Here, the function goes from increasing to having a 0 slope to decreasing. So we have a relative max at x equals positive square root, or 2 times the square root of 2. So say that by the first derivative test, f has a relative min of f of negative 2 and the square root of 2, which is some value. I don't know what it is. At x equals negative 2 root 2, and f has a relative max of whatever that y value is at positive 2 root 2 at x equals positive 2 root 2. So these x values are the locations where the relative min and relative max occur, and then the y values are the relative minimum and relative maximum value of the function. Now, if you want to, you can find those numbers relatively easily. Y was equal to x times the square root of 16 minus x squared. And x equals plus or minus 2 times the square root of 2. It's actually the square root of 8. That was the square root of 8 that was simplified. So if I want to evaluate this function at square root of 8, we're going to have square root of 8 times this expression. And then we'll have negative square root of 8 times that expression. And so we get square root of 8 here times, this is 8, 16 minus 8 is 8. So we get 8 for that value. And here we've got a negative square root of 8 times square root of 8, which is negative 8. So the relative minimum is negative 8, and the relative maximum is positive 8. And it's obvious that when we plug in x equals 0, we get 0. So I don't know exactly what my function looks like. Not without a calculator. This is not a standard function that we're all familiar with, but it's built using standard functions that we are familiar with. We know at x equals negative 4, and x equals positive 4, our function value is 0. And we know at x equals 0, the y value is 0. And then we have at x equals plus or minus the square root of 8, the y values are equal to 8. So we'll have an 8 here, or 8 and negative 8, sorry, 8 and negative 8. And I don't know what 2 root, or the square root of 8 is approximately. Square root of 8 is going to be a little bit less than 3, right? And the square root of 9 is 3. So I'm going to go here. So this is 2 root 2 and 8. And over here, we're going to have negative 2 root 2 and 8. I don't know the details, but I think it's probably going to look something like this. Now, remember what we found. We said our function is decreasing on this first interval, on the interval from negative 4 to negative 2 root 2. And then it's increasing from negative 2 root 2 to positive 2 root 2. And then it's decreasing from positive 2 root 2 to 0 or to 4. So that is consistent with what we calculated here. And then using the first derivative test, we found that we had a relative min and a relative max at these locations. To find those values, we plug the x values into the function to find the corresponding y values. Find the y values, and then we plot the points, and then we expect this to be our graph. So let's look at the function online on Desmos and see if it looks the same way that we expect it to. So when we graph the function on Desmos.com, we see pretty much everything that we saw on paper. We've got y equals x times the square root of 16 minus x squared. Square root of 16 minus x squared can be written as 16 minus x squared quantity to the 1/2 power. When we compute the derivative, we get this. We've done all that calculation on paper. Now when we set that derivative equal to 0, and that happens when the numerator is 0, we get x equals plus or minus the square root of 8, which is plus or minus 2 root 2. That value is approximately 2.828. So we've got 2.828 and negative 2.828 is approximately those two x values that correspond to our critical values of the function. Now, when we're trying to find the intervals where the function is increasing or decreasing, what we're looking for is for the function, the sign of the derivative function. We know that when the derivative is negative, the function is decreasing. When the derivative is positive, the function is increasing. So when we actually look at this picture, we can see that it's decreasing on this interval, increasing on this interval, and decreasing on this interval. You might say, well, how can I find that without actually having the graph itself? Well, we can analyze the signs of f prime on the intervals defined by our critical values. So our critical values were that plus or minus 2 root 2, and then the denominator is equal to 0 when x equals plus or minus 4. So those are critical values as well. Remember, critical values are any x values where the derivative is 0 or the derivative is undefined, and they have to be x values in the domain of the original function. So we get these 3 intervals: the interval from -4 to -2 root 2, the interval from -2 root 2 to +2 root 2, and the interval from +2 root 2 to +4. So when you do that, and you look at the signs, you find that f prime is negative, then positive, and then negative. You can also look at the graph of f prime. So here's our f prime graph. It's this white graph. If we might be clearer if we get rid of the graph of the original function. We see that derivative value, or the derivative values, are negative on this interval, positive on this interval, and negative on this interval. So that means the original function is negative, so it's decreasing here. Positive here, or the derivative is positive, so the function is increasing, and then the derivative is negative here, so the function is decreasing. So we see on this interval from -4 to -2 root 2, function is decreasing when the derivative values are negative. When the derivative values are positive, the function is increasing. And then when the derivative value is negative, the function is decreasing. So all of that is consistent with what we would expect just by looking at the graph of f prime. We see that f prime is equal to 0 when x equals plus or minus the square root of 2 over 2, or plus or minus 2 times the square root of 2. Sorry, it's not in the denominator. And so that's our function. Now the question said, find the intervals where the function is increasing or decreasing. We can see it's decreasing here, increasing here, and decreasing there. And the intervals are these intervals. We wrote them down using interval notation on paper, and we're using sort of less than or equal to signs on Desmos. And then as far as the first derivative test is concerned, since f prime changes from negative to positive at this x value, we know we have a relative min. So when we evaluate the function at x equals -2 root 2, we get y equals -8. So the relative minimum value is -8. And it corresponds to that x value -2 times the square root of 2. And the same thing is true on the other side where y equals positive, or when x equals +2 root 2, corresponding y value is +8. So we've got a relative min here because the f prime goes from negative to 0 to positive. And then we have a relative max here because f prime goes from positive to 0 to negative. So that's it. It's a first derivative test. And it allows us, or we also know how to use the derivative to find where the function is increasing or decreasing.